I'm talking about form finding. We had already a presentation about this morning. And we are talking about structures. Well, we can maybe, these kind of structures. What is common to all of them is that, contrary to classical, say, solid structures, they do not have a reference configuration. So we cannot define in a reference configuration for these structures in two senses. Of course, if you take a catenary or a cable, we can define infinite reference configuration. If we take a cable, we can always lay it on the floor in any form. Any one of these can be a reference configuration, which is stress-free, and any motion that brings this, from this configuration to the hanging chain will be admissible. So, but if you talk about 2D surfaces, membranes, you do not have a reference configuration either because the membrane is not a proper shape, but also if you remove the membrane from the support and you lay it on the floor, this configuration will not be stress-free, and this is a big problem. So we have some way a change of philosophy. So we have to think about elements that do not have any reference configuration, and our goal is to find a configuration that satisfies equilibrium and some other constraints that we will see in a moment. Now, the interest about form finding of one-dimensional, two-dimensional structures is not only for large structures. It's also very important for microstructures. This is something, is a Zheng, is a Chinese scholar who proposed to build microstructures made by assemblage of minimal surfaces. And these solids, these metamaterials, have very, very interesting mechanical properties. And we'll see that minimal surfaces are surfaces of optimal shape in the sense that they have isotropic stress state. So it's important for many reasons. How can we define the process of form finding? So what is given? Well, we have some element, some system, and we know the topology of this system. For instance, from the big 2D surface, we have I don't know, the edges, the connections, the connectivity, the holes, maybe a hole, one hole, two holes, or if we have a net, we have the connection between all the elements, and so where the points where they join. Some fixities are given, some edge built in or some points and so on. But we also need some additional constraints, general additional constraints either on the stress state or on the geometry. And eventually some loads, self-weight, for instance, or other loads. And we have to find a configuration that satisfies equilibrium subjected to the constraint I've said before. The importance of the constraints is very big. Generally, the problem of form finding is undeterminate. Means you can have infinite solutions. Properly assuming constraint can reduce the set of feasible solution. If you enforce too strong constraint, there might be also impossible solutions. So the problem may lose definition. Okay, the background, everything goes back to the experiments that made in Stuttgart with the stop films, and then probably the first real application was done in the Olympia Stadium of München before the Olympics, where they built this for building this system, Scheck developed a very famous method called force density method, which will be the starting point of this work, because the one is the most used. It's not the only one, but the one is more clear from a physical point of view. And this force density method has received many improvements. Originally was devised for monodimensional structures, cables, and later on was extended to 2D structures. Actually, by Bletzinger and his co-workers is in München. Actually, one of the motivations of this interest is that Leopoldo Greco introduced me to this problem many years ago. Then we put it on the side. We did other things, computational mechanics, shells, beams. But this has always been underlying. And the problem is that when we read the works of Bletzinger, actually, at the beginning, I could not understand what he was doing. And the problem is that he uses a language of continuum mechanics, which has to be interpreted. And that's one of the background of this work. So this is the original idea. Probably all of you knows about it. The original idea is to build. Was applied to networks. So networks of trusses, cables, and so on. The original idea was to build equilibrium equation. If you refer to network of trusses, a typical equilibrium equation is the one which is written here, which is a linear equation, of course, in the actual forces, which are unknown. Non-linear in the position of the node, which are unknown, because we do not have a reference configuration. The equations are as many as are the nodes coordinate, the unknown coordinates of the node. So the idea with Scheck was very simple. Let's linearize this equation in the position of the nodes, and introducing a quantity that's called force density, which is the ratio between the stress and the length of the truss. But in this way, you find what solution do you find? Well, changing the force density. You find the force density, you find the solution, you find another force density, you find another shape. So the idea was to enforce some constraint, for instance, on the length of the elements, or on the stress, or the structural force on the element, and solving it iteratively. This is, for instance, an example. This is, there are two examples actually here, just a simple truss, and you can enforce either that the length of the length of the truss of this framework is minimal, or that the actual forces are all constant. It's well known that in the first case, if you enforce a minimal length, you have a solution with constant actual force, and this one. Okay, there's another condition when you enforce to minimize the square of the length, which is, I don't know why the slide is disappeared, but anyway, those are classical theorems. Now, let's try to generalize this idea to 2D surfaces. So the idea is that we start with a topology. So we may have with the parametric domain with some two coordinates, this square, and this application, the map, it points to the position of the membrane. On the membrane, we can the position is unknown, of course. The membrane is embedded in a space where we can define the local metric, the contravariant metric we will also need. The determinant of the metric, the square root determinant of the metric, is the area element. Now, that is all what we need for the process for finding of a membrane. However, sometimes, and that's what confused me very much with Bletzinger works, we can also introduce another configuration, so a working configuration arbitrary, has nothing to do with a stress-free configuration or a reference configuration. We just can refer all the quantities, for instance, deformation, stress, and so on, what we find on the equilibrium configuration to some other arbitrarily defined the reference configuration. So that such that there is a continuing transformation from this arbitrary configuration to the equilibrium one. I will indicate with a 0 this arbitrary configuration. It completely is not necessary, but some cases can be useful for better understanding some results. And without the 0, the equilibrium configuration, the unknown equilibrium configuration. The one with the 0, we have to talk about something which is known. For instance, typically, how we proceed. I will not show now how we do the form-finding procedure, but what we do, we start with a drawing in Rhino. The drawing in the Rhino is, we reproduce the topology of the membrane. So there are some fixed edges, for instance, and then the edges are joined by any line. This will be this original arbitrary configuration where everything is known. Okay. Just in order to fix the idea, C will be with capital C, I will indicate the pullback of the metric of the equilibrium configuration on this arbitrary configuration that we have set, the one with the 0. Okay. So C is the metric of the reference or the equilibrium configuration, but pulled back on this arbitrary configuration. Now, we want a variational formulation, so we define a Lagrangian. Lagrangian is this one. It's the sum of internal energy, or external energy, plus constraints. This is very simple. Internal energy, or now, the internal energy has something to say. We have an element, a membrane, or some cable net, something where we have self-stresses. So we have to take into account the energy of the self-stresses. So the first contribution, this one, this integral, is the potential energy of the self-stresses. Is the dot product between the Cauchy stress and the metric of the equilibrium configuration. Eventually, we may have some elastic energy if we consider the formable membranes. But if I have time, I will tell you later on that this is very difficult to do. And I don't know if you have time. And minus some reference internal configuration. Most of the cases are completely arbitrary, so when you do the variation, it disappears, so it's just some reference level. Analogous you do for the external work if there are loads. In this way, you can consider also heavy membranes, for instance. That's here. The consideration of the strain for finding concerns another problem, which is the materialization problem. So how then you have to realize the membrane, because when it is subjected to self-stresses, it deforms. So the membrane you have to actually cut is not the one that you have found with the form-finding process, but this is a completely different problem. I will not talk about it. Okay, the constraint that can be posed on the stress state or on the geometry. Now, let's start with the first example, which is the most common. A membrane, inextensible. As I told you, the materialization problem is another problem. I will not talk about it. With some constraint on the stress state, so some function, at a scalar, tensor function of the stress, f of s, of sigma. The Lagrangian then becomes the sum of the internal energy, the external energy of then we enforce the constraint with some Lagrangian multipliers called lambda. And this is the duality product. It depends on what is the constraint. If we make the variation with the Lagrangian, we have the variation with respect to the position gives the equilibrium equation, the weak form equilibrium equation. The variation with respect to the Lagrangian multiplier, of course, enforces the constraint, and the variation on the stresses, because this is a three-field functional, gives a condition that identifies what is the Lagrangian multiplier. Basically, it is a okay, the last equation is something missing. Huh? This is wrong, because when you make a variation of the stress, is also a variation of the first integral. So this variation tells you that this Lagrangian multiplier is a deformation. It's something to do with the deformation. Depends on what is the constraint, but it's a kinematical condition. Now, this is what we need. We can proceed because in this case we have as unknown the position, the stress, and this Lagrangian multiplier. However, it can be also useful to pull back all this formulation on this arbitrary initial configuration, the one I have drawn on my Rhino computer program. So we pull back everything. The pullback of the metric is what we call C, so it's a standard Cauchy metric. The pullback of this Cauchy strain is the second Piola stress tensor. And so we can reformulate everything in this reference configuration. In the reference is arbitrary configuration. And in this case, I will call capital lambda the Lagrangian multiplier. Okay, I started this. You can do the same. So this is even in a three-field function. The variation these give you some nonlinear equation for finding these three fields. I will show later how then we proceed in order to compute these three fields. Oh, now one advantage of doing this pullback is that now it's in the entry appears the determinant of the arbitrary metric, which is known. So it's something you don't have to make variation on it. But maybe useful, simpler, but is not essential. Constraints on geometry. There are also there can be constraints on geometry also with membranes, but the most common case is cables, catenary of fixed length. It's a very simple example, a toy example. So again, we have this P is the placement of the catenary on the self-weight. P0 is some arbitrary, again, configuration that satisfies the constraints or the hanging points. Well, there are some loads. So Q or Q0 by conservation of mass, of course, it has to be unchanged in the two configuration. And in this case, we can enforce the length. We want the catenary as a length, a fixed length. In this case, we have this functional, where the first term is the internal energy. And as you can see, in this case, the actual force is therefore as the meaning of the Lagrangian multiplier that enforces that the length of the cable must be the assigned one. And then you may add also elastic energy. In this case, it's possible. Anyway, here it's possible because it's physically, you can you have the cable, you hang it, it stretches, but you can return to the unstretched configuration. So it's easy to, there's no incompatibility in this process, so it's easy to take into account also the deformation, the elastic deformation. Anyway, going to also in the case in the case of an extensible cable, so the formulation reduced to this one. It is a two-field formulation in this case. The first one is making the variation, the variation with respect to the actual force is enforce the constraints. Also, this must be okay. There are some mistakes here, some square root missing, and doesn't matter. And the variation with respect to the position gives the equilibrium of the final configuration of the form we have to find. From this variation, automatically appears the force density, because when you make a variation of the norm of the tangent, it comes out this n over the norm of the tangent, which is force density. So force density automatically stems out from this variational principle. We do not have to postulate it. Okay, well, no problem. Now, solution methodologies. Typically, force density method has been applied adopting a solution strategy which is done by successive approximations. As I told you before, we assign something initially, then some force density, and we correct it iteratively in order to enforce the constraint we want to impose. So this is what is typically done with force density method. Blessing calls it updated the reference strategy, because Blessing also refers to reference configuration, which is actually is the trial configuration. Has some advantages. For instance, the force density must be positive, because we have we are talking about membrane, so we have the stress must be positive. And this is automatically accounted for. However, there are also many disadvantages. The first one is, I'll show you that there might be numerical problems. The convergence is very slow, very, very slow. You need sometimes hundreds of iterations in order to find, depends, of course. And the worst problem is that there is not a clear stopping criteria. What is the, how do you know when you have found your solution? Because you do not have a minimum condition. So you do not know when to stop. And I'll show with some problem. Using the mixed formulation I've shown, okay, which is practically an extension of the Ueshizu principle. So we have to solve a nonlinear set of equations. We can use standard methods, Newton-Raphson, for instance. This convergence is quite fast, robust. There is some small problem. We cannot be sure that in the iteration the stresses keeps positive. And if it is not, we go into trouble, because this is a constraint. Actually, we should impose another constraint, that stress are positive. We did not do that. Okay, for simplicity, but it's not a big problem. You can enforce it with some augmented Lagrangian strategy, which we have not still implemented it, but we can be done. Okay, and what are the convergence criteria? Well, if you have Newton-Raphson, the residual, when the residuum is smaller than the tolerance, you stop. So it's very clear how you stop. Okay, now some example. First, for the easy problem, the catenary, the heavy catenary. This is missing the drawing is just a hanging chain with the two different points at two different height. This is the force density method, so the one done by successive iteration, and we have used. There's some slide missing. This is Leopoldo false. We are discretizing the structure with the splines or NURBS, so in order to guarantee continuity. So this is the example made with NURBS of higher order. This order 1, so just a linear polynomial. It seems everything works, but if you look at this, this is a convergence plot what gives the error on the length, I guess, or on the placement. This is a case where we know the exact solution, so we can evaluate the error. The error for is a function of the number of elements, and you see that the convergence is not quite nice. Sure. Worse, when you go to higher order of polynomial, you see that This is the error on the length. Yes, on the length was or on the position. Anyway, I don't remember. But and see that it goes to a minimum and then it climbs again. So when do you stop? If you know the solution, of course you can check the error, but usually you do not know the solution. So you do not know when to stop. And it's not guaranteed that if you make many iterations, you find the best solution. So this is one big problem, apart from this very bad convergence. Another big problem, this is the plots of for some polynomial degree of the actual forces. They have great oscillation. Well, these are different iterations, but anyway, even in this case, we have oscillation. From an engineering point of view, this is bad. You do not want this. Okay, it's the same. If you improve the polynomial degree, it's slightly better, but still there are oscillations. And this is a very, very, very simple problem. But can you imagine when you do some more complex problem? Okay, this can skip. Now, maybe no. Now, when no, okay, this is the mixer formulation, as we have already seen it before. Now, this is a two-field formulation. Now, this is the mixer case. We have to interpolate either the position and the actual force, because it's two-field formulation. It's a mixer problem. So Bretzi taught us that when you have mixed problem, you need different degrees of interpolation for the primary variables and the dual variables. So we use polynomial of order P, splines of order P for the position, of order P minus 1 for the actual forces. Actually, the implementation has been done with using Bezier extraction. So we work on the elements with the Bezier function, and then we extract from it the spline. But this is technical stuff. So we do all the variation. In this case, you have to evaluate also the second variation, because you need the Hessian matrix in order to implement the Newton iteration. This is don't look at the last column in a row, because it's a particular case. But if you look at the first two rows and columns, this is the standard Hessian of a mixed problem. In the case you add also elasticity, so you consider extensible cables, this term here is not zero, so it can be also condensed, this formulation. In the case of you have inextensible cable, it is zero, so the formulation cannot be condensed, but it's also, again, technical stuff. And these are the results using some other polynomials. You see, as we expect. Now, of course, the error is dominated by the tolerance you are setting. But once you have found, you have reached your tolerance, okay, you can go on. You can make more iteration, but you are sure that is the solution. You find the solution, and convergence is quite smooth, quite nice. It's also maybe the theoretical one. We do not know what is the theoretical rate of convergence for this kind of problem. It's nonlinear. So, well, these are some drawing of the placement on the actual force. This is for the degree 1. This is degree 2. These are the drawing of the placement of the actual force. Degree 3, again, the convergence is pretty. The red line is the force density method. The black line is the convergence of this mixed method, which is rather more accurate. And also, as you can see, actual force has no oscillation at all. So this is very important from an engineering point of view. Okay, this is 4. Okay, fine. This is another example. This is a slack net of 5 cables. Five cables, and the plots show the actual force on the cables. Black line is the mixed method. The zigzag line is the force, the solution obtained with force density method. Now, second problem, which is more interesting actually, membranes, and also we are talking about minimal surfaces. So minimal surface, I told you, is quite interesting. They are defined as a surface which has zero mean curvature. So, and a Gaussian, a negative Gaussian curvature, but mean curvature is zero. This is one of the definitions of many. And there are other equivalent definition. Minimal surface, the name comes from the surface, a critical point for the area functional. It's not a minimum, it's a critical point. And also it's the equilibrium configuration of a soap bubble. So it's a surface which has a homogeneous isotropic state of stress, which is, from an engineering point of view, the most interesting feature. So what is the constraint we have to enforce in this case? For example, the Cauchy stress has to be isotropic. So P, some stress, which we take 1, of course, times the contravariant matrix. Sigma is a contravariant tensor. Or, if we want to pull back from some arbitrary configuration, that the pure tensor is given by the pullback, the contravariant matrix, C minus 1, and this is the ratio of the area between the the unknown equilibrium configuration and this arbitrary initial configuration. This is the Lagrangian. The specific how it specifies in this case. This is a constraint. This is the one in parentheses, which leads to a 3 fields Uwashitsu type principle. In the unknown is the position, this stress, and this Lagrangian multiplier lambda. If we make the variation, actually, they are not written here, but the Lagrangian multiplier exactly the meaning of the metric C. That's in solution they are the metric. So I told you it's a kinematic constraint, exactly as happens with the Uwashitsu principle. Now we can manipulate a little bit this equation. This is interesting. This is not from a computational point of view, but from a, it's interesting to see if we manipulate this equation. We introduce the Eshelby tensor, and multiply this Eshelby tensor by the contravariant matrix. We have the contravariant form of the Eshelby tensor with all indices up, which is called E sharp, this one. This is an equal sign you're missing. We can reformulate this principle with the Eshelby tensor, and we have a very interesting formulation that tells us that the divergence, we make the variation, we have a divergence of the Eshelby tensor must be equal to a driving force, which is the variation of the area. So this is interesting because the equilibrium we have it that the driving force, we're finding a shape with the minimal area. So the driving force is the area must be minimum. So there is the force that drives the solution towards the minimum area, and the internal force is this contravariant Eshelby tensor. In solution, this contravariant Eshelby tensor is 0. This is interesting as an interpretation. Can also be implemented in this way. Anyway, we have followed the classical, the physical, the one with the stress, and we can introduce this tensor, multiplying the pure tensor times the area element, and this is the tensorial density. Is the one that Bretzian calls force density. In the case of membranes, this is a tensorial density. We call big mu, like in the case of cables, force density. We can reformulate the principle in substituting this tensorial density to the stress. It's very similar. It's more convenient from a computational point of view. And so we can solve this 3-field interpolating the three fields of these three fields of unknowns, of variables. There are some problems also in this case because we have to find the initial solution which is a good initial solution. This can be done for instance making a first step for finding. And there are some other problems related to the fact that we have not enforced the positivity of these Lagrange multipliers, which are the force densities. And in order to avoid problem, we use a kind of homotopy iterative procedures. Anyway, again, it's technicality for the implementation. But okay, we can do all variation, blah, blah, blah. First or second variation, the Hessian matrix is this one. Actually, these terms, H23, H32, are just Gramian matrices. So this part here, the one that concerns the constraints, is invertible. H11 is the second variation with respect to the position. It turns out, I have no proof for this, it turns out to be always well definite. Not only positive definite, but also with a very small conditioning number. So it's very well defined matrix. I have not a general proof for this. And also this matrix is H12, that are the rectangular matrices of the constraints that comes out with the mixed formulation, are always full rank. So seems to be a very robust formulation. Anyway, we have to find a way of proving it in generality. Again, interpolation is mixed, so p degrees for of the splines for all nerves for the position, and 1 degree less on one direction for the stresses according, if it's S11, S12, S22, in one or other direction, the interpolation degree is decreased by 1. Okay, application is a catenoid. This is a form, or this is a quarter of a catenoid, of course. This is the exact solution is known, so we can test the solution we obtain, and so this is the exact area. These are the degrees of interpolation used for this placement and for this stress component. The same interpolation is used also for the Lagrange multiplier, the kinematic Lagrange multiplier is capital lambda. And these are the convergence plot for the, in this case, for the residuum for some different values. So this zeta parameter, this zeta is the one which helps convergence, but for instance, the last one is almost 1. We get quadratic convergence. That means the solution, the formulation is correct, because in Newton we expect quadratic convergence, and we get quadratic convergence. And that's here is written what I told you before, that the ratio between maximum and minimum eigenvalue remains controlled. It's quite small, actually. Here is the trace of the stress, which is 2, which we apply the stress sigma equal 1, so we find the correct trace, absolutely uniform. Of course, it is a different iteration, and the final iteration we get the correct solution. And this is the convergence for the both that probably is the position. Again, we know the exact solution in this case. The convergence, and using with the black line again is the mixed solution. With the red line is the updated reference strategy, which is not too bad in this case. It's not too bad, so slightly less accurate. The problem is that in this case we know when we have to stop, because we know the exact solution. Generally, we do not know. You can do other things. For instance, this is a minimal surface with the pentagonal catenoid with the cables rather than fixed boundaries. which you can combine cables and membranes. This is an example I asked the student to do. This is a nice membrane that was built in Kazakhstan because the president of Kazakhstan wanted to celebrate his birthday building this very huge 150 meters tall membrane. And to see, this is not a minimal surface actually. Now, in this case, there are other problems. You need to enforce kinematical constraint, for instance, the length of some geodesic or a length of a meridian or something also. So this is different problem. I'm not going to talk. This is interesting. This is a minimal surface called the parametrical Costa surface. It's parameterized according to the diameter of the inner circle to the outer circle. And this is one thing that shows, these are all solutions for minimal surfaces. And this is one thing that shows what is the problem with the updated reference strategy used so far. This first line, there are three different shapes, and this plot is the plot of the area towards the number of stress or steps of updated reference strategy. The minimal surface, which is this one, it stays up here. I told you the minimal surface is not the surface of minimal area. It's a surface where the area function is a critical point, so a flex point. And this here. If you use updated reference strategy, you cannot find this point. Maybe. If you do all plot, you can try by chance to find something. Using the mixed formulation, you find, because you enforce that the stress state is isotropic. So you find directly that point, that shape. Okay. Conclusions. So the mixed formulation can be effectively solved with the very reduced, the iterations are very small, very few iterations we found the solution. And then we have a clear convergence criteria. I've shown the case of a minimal surface, which is the most common, but you can enforce other constraints on the stress state. The formulation is a Lagrangian, so you can introduce any kind of constraint you need. Even inequality constraint. We have not done that yet, but you can enforce inequality constraint. This is very important because when you have a membrane, sometimes you cannot have minimal surface, you can have other surface. But what you want is that shear stresses are small because shear stresses generate wrinkling. So what you want to do, and that's a very interesting application, you want to keep the deviatoric part of the stress as small as possible. So in order to avoid wrinkling, which is, of course, reduce the membrane stiffness. You can enforce also this constraint, and it seems to be very, very interesting. You can enforce geometric constraint, like in the tent of the Sultan of Kazakhstan, with some constraint on the length. Okay, as future development, you can. There are more efficient formulation that may be done not interpolating the dual variables, but just enforcing locally the constraints. But this is, has to be investigated about the efficiency and the robustness of this other formulation. Okay, I think I finished. Okay. Yeah.
In the capillary problem, you said that you added some extensibility.
No, in the example I've shown, no, there's no extensibility.
But also not for stabilizing the solution,
No. Well, stabilize the matrix because it becomes invertible. Also, you can condense it, but I don't think it stabilizes the solution.
And then you should start in a configuration where the constraints are valid. How are you dealing with that problem?
Yes, but what do you mean, the constraint? What constraints?
I mean, you have this in the catenary, you have the inextensibility.
Yeah, that's what the case I've shown. I enforce the length of the catenary.
Yes, but
so in the case you have extensible catenary, you have two configurations, which is the equilibrium final configuration, and now that's the real reference configuration because the unloaded. You have to make two variations. You have to, and because you have the
configuration is with another length.
No, the static configuration, anything can be a straight line. So this like the starting point of Newton process. You have start with something, which does not the length constraint is imposed variationally. It's not enforced from the beginning.
So you could start with a
anything. Yes. Usually we start with a line.
Yeah.
So you cannot do it. That's started the idea. You start. It's not to be too far, of course, but it's just the radius convergence to Newton. Then one of the conditions is the one that forces the length. Actually, it is easy to enforce the length, enforcing that equal length elements of equal length. This is it gives you more regular solution. This is So you say I divided my catenary in 10 elements. Each one is 1/10 of the original, of the researched length. This easier to enforce. This is the length of each element, the more stable. The way you have some element very long, some other very short, can be some numerical problem. But anyway, it's technicality. This is. Yeah.
Massimo, when you spoke about the HMB configuration test, it was used for computational reasons or just to give a mechanical interpretation?
Mechanical interpretation. Well, actually, also from a computational point of view, it could be easier. Again, it's not very easy, but we have not done it. But looking at it, why we did not win? I added afterwards. Looking at it, might it be easier to start from this formulation and just to interpolate HB. No, it was a mechanical interpretation.
So regarding the reference configuration you mentioned regarding the Letzinger formulation, I always understood it as a way to introduce a strain distribution that you need for the variational formulation, but then it disappears in the final equations, and because also the strain usually disappears.
Yeah, it's the problem that
your interpretation.
No, I think Bresky is very confused because he talks about gradient of deformation. Of course, it is no deformation here. So it's just what he's really talking about is a map from one configuration to the next one.
But you need a strain, however, to formulate the variation.
You have no strain here. The membrane is inextensible. No strain at all. This is a transformation. You have a map, another map. You have a transformation. That's no strain. That's the problem. It's confusing because you're talking about deformation, but it's not a deformation. It's a transformation. Anyway, it's
And also, do you always need a constraint? Let's say you're using for minimizing area problem. You're using a constraint on the area. But in that kind of problems, you always have the whole boundary of the membrane to be fully constrained.
You can fix some points also.
But you also showed a case in which you have only some points of the boundary that are constrained, and you have to introduce, however, a cable
yes.
to constrain the boundary.
No, otherwise the solution is degenerate because you don't have.
You are minimizing the area. If your problem is different, let's say you are analyzing a tensile structure in which you don't need to minimize the area necessarily.
I don't know, if you're looking for a minimal surface and you don't put cables, it degenerates in lines. So the solution is in the area. If you minimize something else, I don't know what happens actually.
Do you need to minimize the area in
No.
or you can solve it?
No, I mean, that's the application which is usually done. You think you can imagine to enforce other constraints. That's already at the beginning. If you make wrong constraints, the problem is you have a set of equilibrium solutions for the position, a set of placement that satisfy constraints. If this is to set, have no intersection, you don't find anything. So it's like with the limit analysis, equilibrium and constraint. You have to find when two set have a common point, a common tangent. You have this one only solution, but usually in this case, it's not. Can be that can be, but you know not always. In the case of minimal solution, you have just one, but in other cases, you may have very many solutions.